before we proceed to look at further reactions in this chapter, we need to revisit keto enol tautomers. It's something that's going to come up in some of the reactions that we cover as we go through this chapter, the rest of this chapter. So remember that the keto form is an aldehyde or a ketone, and typically speaking, this predominates at equilibrium. So, in the case of acetone, I think it's about 99%, and the enol is about 1%. Recall it's called an enol because you've got your double bond, your alkene, and you've got your alcohol over here. So there are some situations that arise that can shift this equilibrium a little bit. So I want to talk to you guys over here on the side about some exceptions. So let's take a look at the first one here. So what if we had something like this? Right, so this is the keto form of that molecule, and we'll go through and show how this occurs, but this is in equilibrium with the enol form. So the enol form is going to have a double bond with an OH, right? There's your ene, here's your ol. So when you look at this and you make a guess on what predominates, the reactant or the product, you probably all are going to say, well, the product here are the enol form. And that's because you have resonance there, right? So this is at like 0%, and this is at 100%, essentially. So there's some other things that can help too. Hydrogen bonding, for example. So if you look at this diketone, and if you look at the equilibrium enol form of this thing, here you would have your ene and your ol here. So if you look at the enol form of this, there's your carbonyl, here's your oxygen, and what happens is that H hangs out over here, and we get hydrogen bonding occurring right there. Right, so here we have H bonding, which helps stabilize your enol. So again, here's your enol, here is your keto form, and here you're about 24% and about 76%. Right? That's kind of the idea there. Well, let's take a look at the different reaction conditions here that give rise to different types of reaction pathways. So we're going to look at base-catalyzed and acid-catalyzed keto enol tautomerism. So you may recall this reaction from first semester where we take an alkyne and we hydrate it. And so we get here our enol, and then now what happens is we have a basic catalyzed mechanism to form the ketone. So looking through here, we're going to grab this H. We'll have an O minus right there, rather. Right, we have our other enolate on here, and then on that last step, we're swinging around and grabbing a hold of that H to give us, it's an aldehyde, but we still call this the keto form. So let's see if we can go backwards. So let's take our keto form here and see if we can write out what our enol form is. Now, the cool thing is that this last step here, so if we go this direction, we gained an H. So moving backwards, we have to do the opposite of that. We have to lose an H. So we're going to swing around and grab one of those H's. Now, that'll give us this, which is our, this is our enolate. And this has a resonance structure. So we can swing around and we can do this. That'll give us this. And then the last step of this thing, right? So we're back to here. We're going to go this direction. Right? So again, looking forward, you lost an H. Moving backwards, we need to gain one. It's base catalyzed still. So we're going to gain it from water so that we can make hydroxide. So we're going to get our enol back. And there we have it. Well, what about acidic conditions? Well, let's take a look at it. So acidic conditions, mechanism's pretty straightforward. So again, here we're going to start off with that same alkyne, and we're going to hydrate it in the presence of mercury and sulfuric acid. That'll give us our enol, and now we have acid catalyzed mechanism here. So the first step here, if we want to write that out, let's write out H3O plus as H plus comma H2O. So first we're going to do this. We're going to grab an H. So this CH2 is going to become a CH3, right? So you get a Markov-Nikov addition there. Next we have resonance. So we're going to swing these around and make our carbon-oxygen double bond, giving us this. And the last step is we're going to grab that H there to give us our keto form right there. Right? Not too tough. Well, let's see if we can go backwards. So let's take our acetone here, and let's see what we're going to do. So look at the last step of our forward reaction was losing an H. So then the first step of this reaction is going to be gaining an H. So we're going to swing around and we're going to do this. That'll give us this, right? And then that has a resonance structure. So we're going backwards even more now. So here, there's your OH. There's your plus charge on that. And then let's look and see what happens. So, all right, moving this direction, we gained an H. So moving backwards, we need to lose an H. Now, where did the H get gained moving forward? That CH2 became a CH3. So I'm just going to write this here as a CH2 and then stretch that out as an H there. Okay, so then the last step of this reverse reaction is that we're taking water and we're going to grab this H and plop those electrons down between the carbon and the carbon there to give your ene back of your enol. So there's your ene and there's your ol. So now we have our enol back from the keto form.